Hello everyone, today we're going to look at how insertion works in an AVL tree. So let's get started. Now, if you're new here, please don't forget to like, subscribe, and most importantly, click that notification bell if you enjoy this content. An AVL tree is a binary search tree in which for every node, the height of its left subtree and the height of its right subtree have a difference of at most 1. So the height of a node is basically the number of edges in that node's deepest A to leaf path, where A is the node we're looking at. So for example, if you're looking at the node 70, the number of edges in its deepest A to leaf path is going to be 0, because there are no edges. So its height is going to be 0. If you look at 80, there's one edge in its deepest A to leaf path, so its height is going to be 1. If you look at 60, there are 3 edges in its deepest A to leaf path, 60-30, 30-20, and 20-10. Or alternatively, it could be 60-30, 30-50, and 50-40. So that's how we're determining the height of some given node. Now the height of an empty tree is going to be represented as -1. Now let's see what insertion looks like. So to insert an AVL tree, we're going to use something called the balance factor. And all the balance factor is the height of the left subtree minus the height of the right subtree. Now there are 3 valid balance factors, -1, 0, and 1. -1 means that the right subtree is higher by 1 than the left subtree. 0 means that the left subtree and right subtree are balanced, or they have equal heights. 1 means that the left subtree is 1 higher than the right subtree. Now, any deviation from these balance factors means that the tree is not a valid AVL tree. So for any value greater than or equal to 2, or any value less than or equal to -2, means that we have an imbalance and this tree is not valid. So let's go over this AVL tree here. So our leaf nodes have a height of 0, as we know, because there are no edges in its deepest A to leaf path. And our node with value 30 has a height of 1, because there's one edge in its deepest A to leaf path, where A is a node with value 30. Now let's insert the value 40. After inserting this value, we know being a leaf node, its height is going to be 0, and its balance factor is going to be the height of the left subtree minus the height of the right subtree. And its left subtree has a height of -1 because it's empty, and its right subtree also has a height of -1 because it's also empty. And -1 subtract -1 is going to give us a value of 0. And as we know, 0 is a valid balance factor, so the tree rooted at 40 is a valid AVL tree. Now, because we added a node to this path, it means that we're going to have to adjust heights as we go up this path, until we find a point where there's an imbalance, which we'll see how to deal with later on. So moving up to 50, its height is going to increment by 1, and its left subtree has a height of 0, and its right subtree has a height of -1. So its balance factor is going to be 0 minus -1, which is going to be +1. And +1 is a valid balance factor. So the tree rooted at 50 is going to be height balanced as well. So this is completely fine. Now moving up to 30, its height increases by 1, so it becomes a height of 2, and the height of its left subtree is 0, and the height of its right subtree is 1. So the balance factor for 30 is going to be 0 minus 1, which is going to result in -1. And a -1, as we know, is a valid balance factor. So we can say that tree root at 30 is also height balanced. So this is a valid AVL tree. Now let's look at another structure here. So this is another valid AVL tree. And what I want to do is just work out the heights for each node in the tree so that we're on the same page before inserting a node. So our leaf nodes, as we know, have a height of 0. And if you look at our node 20, it has one edge to its deepest leaf, so it has a height of 1. Our node 50 also has one edge to its deepest leaf, so it also has a height of 1. Our node 30 has 2 edges to its deepest leaf, so it has a height of 2. Our node with 80 has one edge to its deepest leaf, so it has a height of 1. And our node 60 again has 3 edges to its deepest leaf, so it has a height of 3. Now that we know these heights, let's insert a node into this tree. So I insert the node with value 100. After inserting this node, it's going to have a height of 0, reason being is because it's a leaf node. Now, because we inserted a node, we're going to have to work out the balance factors to make sure they're all valid, and also we have to increment the heights of each node along this path. So starting at 100, its balance factor is going to be 0, reason being is because -1 minus -1 is 0. If we go up to 90, we have a height of 1 now because we inserted a node to its right, and its balance factor is going to be -1, because its left subtree is -1, and its right subtree is 0. -1 minus 0 is -1. As we go up to 80, its height is going to change to 2. Its left subtree has a height of -1, and its right subtree has a height of 1. Now the balance factor is going to be -1 minus 1, which we know results in -2. So what we have here is an imbalance, because this is not a valid balance factor, right? Our balance factors have to be -1, 0, or 1, meaning that the height between our node's left and right subtree should be at most 1. However, in this case, it is 2. Now, to fix this imbalance, we're going to have to rearrange this subtree root at 80. And this brings us to our next topic, called rotations. Now, a rotation is how we fix this imbalance. we either perform something called a right rotation, which is moving from the left diagram to the right diagram, or something called a left rotation, which is moving from the right diagram to the left diagram. And we'll go over this step by step. Now, because we're dealing with binary search trees, we must preserve the invariant that all nodes to the left of a given node are smaller than that node, and all nodes to the right of a given node are larger than that node. And we can see from both these diagrams, this is the case. If you look at x and y nodes in our left diagram, x is y's left child, so it's smaller than y. If you look at x and y in our right diagram, x is y's left parent, so it's still smaller than y. So that is maintained. If you look at tree 1 and tree 3, in the left diagram, tree 1 is x's left subtree, and tree 3 is y's right subtree. In the right diagram, tree 1 is x's left subtree, and tree 3 is y's right subtree, so everything is consistent there. Now if you look at tree 2, in the left diagram, tree 2 is less than y and more than x, and the right diagram, tree 2 still remains more than x and less than y, so that's completely fine as well. Now I want to go over a simple way to think about these rotations. So moving from the left diagram to the right diagram, which is known as a right rotation, picture your hand on link XY. If you were to move your hand in a clockwise direction, and there was a lock on tree 1, what will happen is that X would move on top, Y would go below, and tree 2 would just slide across to Y's left subtree. And that's exactly what a right rotation is. Now moving on to a left rotation is the same concept. Imagine our hand on the red link XY here, and moving in an anti-clockwise direction this time. If we move in an anti-clockwise direction, and there was a lock on tree 3, what will happen is that Y would go above, X would go below, and tree 2 would just slide across to X's right subtree. And that's exactly what a left rotation is. Now let's take a look at some insertions and how they result in imbalances and see how we can use either a right rotation, a left rotation, or both to fix these imbalances. So here we have the nodes 80 and 70. And we'll first start by working out the heights of these nodes. So 70 has a height of 0, and 80 has a height of 1. It has a height of 1 because it has one edge in its deepest 8-leaf path. Now let's insert the node with value 60. If we insert 60, 60 is going to have a height of 0 because it's a leaf node, and its balance factor is going to be 0 as well, because its left subtree has a height of -1, and its right subtree also has a height of -1. -1 minus -1 is a 0. So all we're going to do, as we remember, is go up the path and fix the heights as we go up. If we find an imbalance, we're going to correct that imbalance by using the rotations we defined before. So let's go through it. 60 we know has a balance factor of 0, so it's valid. So we move up to 70 and fix its height. Its height is 1, and its balance factor is going to be 1 as well, because its left height is 0 and its right height is -1. 0 minus -1 is +1. And +1 is a valid balance factor. So this is completely fine. As we go up to 80, it has a height of 2. But its left subtree has a height of 1 and its right subtree has a height of -1. 1 minus -1 gives us a balance factor of 2, which we know is invalid. So you have to fix this somehow. And that brings us to our very first case, which is known as the left case. So our left case, all we have to do is perform a right rotation on the link AB. And as you remember, picture your hand on that red link and moving in a clockwise direction. And if you do that, 70 goes above, 80 goes to the right of 70, and 60 remains attached to 70's left subtree. And because tree 2 is empty in this diagram, it means nothing will be attached to 80's left subtree. And that'll look like this. Now all we do at this point is update the heights of our nodes A and B. So A has a height of 0, and B has a height or remains a height of 1. And we're done. Now let's take a look at our second case. Here we have 60 and 70, where 70 is 60's right subtree. Now let's just figure out the heights of these nodes. So 70 has a height of 0, because it's a leaf node, and 60 has a height of 1, because it's one edge in its deepest 8-leaf path. Now what we're going to do is insert the node with value 80. After inserting 80, the tree is going to look like this. And as we know, 80 being a leaf node, it has a height of 0, as well as a balance factor of 0. Now going up to 70, it has a height of 1 now, and its balance factor is -1 minus 0, which is going to be -1. And -1 is a valid balance factor. So going up to 60, it now has a height of 2, its left subtree has a height of -1, and its right subtree has a height of 1. And as we know, -1 minus 1 gives us a balance factor of -2. So what we have here is an imbalance. And this brings us to our second case, known as the right case. So in this case, we're going to picture our hand on the link AB, and this time we're moving in an anti-clockwise direction. So if you move in an anti-clockwise direction, 60 goes below left, 70 goes above, and 80 remains attached to 70's right subtree. And that'll look like this. Now all we do is update the heights of our nodes A and B. So A now has a height of 0, and B's height remains as 1. And we're done. This is now a valid AVL tree. Now let's look at another type of imbalance. So here we have 80 and we have 60 as 80's left subtree. So let's work out the height of this AVL tree here. 60 has a height of 0 because it's a leaf node, and 80, as you know, has a height of 1. Now what we're going to do is insert the node with value 70. After inserting 70, it gets inserted as 60's right subtree. So now we're going to update the heights of these nodes going up the path and checks for an imbalance in balance factors. So 70, as we know, has a balance factor of 0. Going up to 60, its height changes to 1, and its balance factor is going to be -1 minus 0, which is going to result in -1, which again we know is a valid balance factor. Going up to 80, its height is now 2. Its left subtree has a height of 1, and its right subtree has a height of -1. So 1 minus -1 is going to result in a balance factor of 2. And as we know, this is not a valid balance factor. So you have to fix this somehow. And this brings us to our third case known as the left-right case. So what we're going to do is start by performing a left rotation on the link BC. So again, let's go through this. Picture your hand on the red link, moving in an anti-clockwise direction. If we move in an anti-clockwise direction, C goes above and 60 goes below. So that's going to look like this. Now we'll update the heights of our nodes B and C. So B now has a height of 0 and C has a height of 1. Now we're going to perform a right rotation on the link AC. So again, picture your hand on that red link. 80 goes below, 70 goes above, and 60 remains attached to 70's left subtree. So that's going to look like this. Now we update the heights for A and C, so A's height is now 0 and C's height remains 1. Now let's take a look at the last case. So here we have two nodes, 60 and 80. Now let's just update the heights for each of these nodes. 80 has a height of 0 being a leaf node, and 60 has a height of 1. Now let's insert the node with value 70. Inserting 70, being a leaf node, has a height of 0 and a balance factor of 0 as well. So now we'll go to 80. 80 has a height of 1, its left subtree has a height of 0, and its right subtree has a height of -1. And 0 minus -1 is a balance factor of 1, which is a valid balance factor. Going up to 60, its height is updated to 2, its left subtree has a height of -1, and its right subtree has a height of 1. And -1 minus 1 gives us a balance factor of -2. And -2 is an invalid balance factor, so you have to fix it somehow. And this brings us to our last case, known as the right-left case. So in this case, we take the link BC, again picture a hand on that red link, and perform a right rotation on that link. So performing a right rotation brings 80 down and brings 70 up, like this. Now we'll update the heights of our nodes B and C. So B has a height of 0 and C has a height of 1. Now we're going to take the link AC and perform a left rotation on that link. Again, picture a hand on that link, moving in an anti-clockwise direction. So A goes down and C goes up. And we finally update the heights for our nodes A and C. So A's height is updated to 0, and C's height remains 1. Now let's take a look at the actual insertion operations for some values. Now before we get to inserting nodes, I want to go over a quick recap on how the insertion operation works. So when we insert a node, what happens if we add 1 to the height of that path? Right, because we're inserting a node to that path. So when we insert that node, we have to go back up the tree checking to see if we created an imbalance, because we're only allowed to have at most a difference of 1 between any two given subtrees. Now when going up the tree, we know that if there is an imbalance, that imbalance is going to be at most 1, right? The reason being is because we inserted one node, and the tree must have been in balance before inserting that node. So once the tree is out of balance, what happens is that once we fix it, our tree remains back to the same height as it was before, or that subtree. So as far as a parent of the imbalanced node is concerned, all it sees is that, okay, you know what, my subtree is back to the height as it was before, so I don't need to update my height anymore. And that's it. So let's go over some insertion operations to see how this actually works. So inserting node 20, it has a height of 0 and a balance factor, as you know, of 0 as well. Now let's insert the node with value 16. Inserting 16, being a leaf node, also has a height of 0 and a balance factor of 0 as well. Now since we inserted a node, we're going to go up the tree and fix the heights. So 20 now has a height of 1, and its balance factor is going to be 0 minus -1, which is going to result in +1, which is a valid balance factor. So this is a valid AVL tree. Now let's insert the node with value 12. So 12 of course has a height of 0 and a balance factor of 0 as well. Now let's update the heights going up the tree. 60 now has a height of 1, and its balance factor is going to be 0 minus -1, which is going to result in +1. And +1 is a valid balance factor. Now going up to 20, it has a height of 2, and it has a balance factor of 1 minus -1, which is going to be 2. And as we know, 2 is not a valid balance factor. And we have to fix this, and this brings us to our left case. Now what we're going to do, as you remember, is take the link between A, B, imagine we have our hand on that link, and moving it in a clockwise direction. So what happens is 20 goes below and 16 goes above, like this. And then we update the heights of 20 and 16. Now let's insert the node with value 25. Inserting 25, of course, has a height of 0 and a balance factor of 0 as well. Now what we're going to do is go up this path and update the heights as we go up, looking for an imbalance. So we'll go up to 20, its height is updated to 1. Now its left subtree is a height of -1 and its right subtree is a height of 0. And -1 minus 0 is going to result in a balance factor of -1, which is a valid balance factor. Now we go up to 16 and update its height. So 16 has a left subtree height of 0 and a right subtree height of 1. And 0 minus 1 is going to result in a balance factor of -1. Now what we have here is a valid AVL tree, so this is completely fine. And there's no need for rotations. So let's insert the node with value 30. So 30, of course, being a leaf node, has a height of 0 and a balance factor of 0 as well. Now what we're going to do is go up this path looking for an imbalance, and if there is one, we'll fix it. And while we go up, we're going to update the heights. So 25's height gets updated to 1, its left subtree is a height of -1, and its right subtree is a height of 0. And of course, -1 minus 0 results in a balance factor of -1, which is a valid balance factor. Going up to 20, its left subtree is a height of -1, and its right subtree is a height of 1. And -1 and -1 results in a balance factor of -2, which we know is an imbalance or not a valid balance factor. And this brings us to our right case. So for our right case, picture a hand on that link AB moving in an anti-clockwise direction. So 25 goes above and 20 goes below, like this. And what we do at this point is update the heights for our nodes A and B to 0 and 1 respectively. And we're done. Now inserting node with value 24, of course being a leaf node, has a height of 0 and a balance factor of 0 as well. Now we're going to update the heights going up this path looking for an imbalance. So 20's height is updated to 1, and its left subtree is a height of -1 and its right subtree is a height of 0. And -1 minus 0 results in a balance factor of -1, which again is a valid balance factor. Now we go up to 25 and update its height to 2. Its left subtree has a height of 1, and its right subtree is a height of 0. And 1 minus 0 gives us a balance factor of 1, which again is a valid balance factor. Now going up to 16, its height is updated to 3, and its left subtree is a height of 0, and its right subtree is a height of 2. And 0 minus 2 results in a balance factor of -2. And as we know, -2 is not a valid balance factor, and this brings us to a right-left case. And for this case, we're going to perform a right rotation on the link BC, and then a left rotation on the resulting link AC. So let's see what this looks like. Again, picture your hand on that red link moving in a clockwise direction. And when we move in this clockwise direction, 20 goes above, 25 goes below, and 24 just shifts to become 25's left subtree, like this. And all we do now is update the heights of our nodes B and C. B's height is updated to 1, and C's height is now updated to 2. Now what we're going to do is perform a left rotation on the link AC. Now perform this left rotation. Again, picture your hand on that red link moving in an anti-clockwise direction. So what will happen is that 20 goes above and 16 and 12 go below, like this. Now at this point, we update the heights of our nodes A and C to 1 and 2 respectively. Now we're going to insert the node with value 21. And of course, this being a leaf node has a height of 0 and a balance factor of 0 as well. Now as you remember, we're going to go up this path, updating the height, and look for an imbalance. If we find one, we'll fix it. So let's do that. Swing up to 24, its height is updated to 1, and its left height is 0, and its right height is going to be -1. 0 minus -1 is going to result in a balance factor of +1, and +1 is a valid balance factor. Going up to 25, its height is updated to 2, and its left height is 1, and its right height is 0. And 1 minus 0 gives us a balance factor of 1. So this again has a valid balance factor. Now going up to 20, its height is updated to 3, and its left height is 1, and its right height is 2. And 1 minus 2 gives us a balance factor of -1, which again is a valid balance factor. Now we insert the node with value 22. Inserting this node has a balance factor of 0 and a height of 0 as well. Now what we're going to do is go up this path, and if we find an imbalance, we'll fix this, updating the heights along the way. So going up to 21, it has a height of 1 now, its left subtree is a height of -1, and its right subtree is a height of 0, and of course -1 minus 0 is going to result in a balance factor of -1. And -1 is a valid balance factor. So going up to 24, its height is updated to 2, its left subtree height is 1, and its right subtree height is -1. And 1 minus -1 is going to result in a balance factor of 2, which we know is not a valid balance factor. So we have to fix this, and this brings us to a left-right case. For a left-right case, we're going to again perform 2 rotations, a left rotation on the link BC, and then a right rotation on the resulting link AC. So, perform this left rotation on the link BC. Again, imagine your hand on that red link there, moving in an anti-clockwise direction. So 22 goes above and 21 goes below, like this. Once that's done, we're going to update the heights of our nodes B and C, and we're going to perform a right rotation on the link AC now. So again, picture your hand on that red link, moving in a clockwise direction. So moving in a clockwise direction, 22 goes above and 24 goes below. So it's going to look like this. And at this point, all we have to do is update the heights of our nodes A and C. And we're done. What we have here is a valid AVL tree. So that's basically how the insertion operation works. Now let's take a look at the time and space complexity analysis. So for the time complexity, the insertion operation is going to be big O of log n. And it's pretty clear here. If we go down the tree traversing to insert a node, that in itself is going to take log n time. Now when we actually insert that node, we're going to have to go up the tree or up that path looking for an imbalance. In the worst case, we don't find an imbalance, so we end up going all the way to the root, which is going to take log n time again. Now as for the rotations, these are all constant time. And in the worst case, we're performing 2 rotations, a left rotation and a right rotation, for either the left-right case or the right-left case. And regardless if it's a left rotation or a right rotation, all we're really doing is manipulating a few references. And that's it. It's a constant number of operations, so it has no effect on the big O. Now let's move on to the space complexity. For the space complexity, it's pretty clear, right? If we're augmenting the tree, that's going to take n extra space if we include that in our space complexity. And if we exclude it, we're going to use a constant amount of space, because the space used by the node is going to be independent of the insert operation. If you enjoyed this content, please hit that like and subscribe button. See you in the next video.